Hello, I am Wolf, and you are here presumably because you spent last Sunday afternoon with us, Sunday, May 18th, where we held a multi-hour telescope workshop. And even though we spent a lot of time together during that in-person session, there were multiple places where I said that we're skipping some content in the interest of time. And I promised you that there would be a video that would fill in those gaps. And so this is that video. All right, so with that, let's go ahead and jump into the details and into the content. We are going to cover further detail on the following topics. One, we'll talk a little more about focusing. So these three here, focusing, image formation, and magnification, rely on ray diagrams. Actually, even the F ratio one over here will. So here we'll look at a bunch of ray diagrams that will talk a little more about how focusing works, a little more about how the image is formed, through the telescope, how magnification works out to be the telescope's focal length divided by the eyepiece's focal length, and then we'll talk a little more about f ratio or f-stop or f-number, because some of this, as I mentioned during the in-person session, can be a little confusing. Once we have that done, we will move on and talk about some more examples about eyepieces and Barlow lenses, then spend a little bit of time on a couple of concepts related to mount mechanisms, because you may run into those when you go mount shopping. And we will briefly mention a new technology that's come into the consumer market relatively recently called strain wave mounts. Then we will close it out by spending a couple minutes on finders and optical filters. With that, let's go ahead and jump in and talk about focus and magnification. Okay, so just to kind of revisit where we were on Sunday, to put things back into context, we had said that the position of the lenses determine whether the image is in focus and therefore provides a clear view to your eyes. The focused image may not be right side up, and the focal lengths of the lenses determine the magnification of the image, right? So we had started here, we had said this on Sunday as well, and now we'll talk about each of these in a little bit more detail. So there will be a bunch of ray diagrams ahead. Ray diagrams can get complicated, so we may cheat a little bit in favor of a clearer story, but that's okay because our goal here is conceptual understanding, and our foundation for that conceptual understanding will be good. So, so each lens, objective and ocular, has its own focal point. We saw that already on Sunday, right? And here, here was the same kind of diagram that we showed on Sunday. Here's the objective lens, here's the ocular lens. Together they form our light funnel. And the objective lens has a certain focal length to its focal point that sits here, and the ocular lens has its own focal length to its focal point that sits in the same spot in this diagram. And in fact, for the eye to see a good image, for the image to be in focus, we want these two focal points to align. And because if we do that, then we end up in a situation where the incoming parallel rays end up being parallel rays coming back out. Now, it always gets a little more complicated if you dig further into the details. In reality, there are other factors that come into play. For example, your own eyeball has a lens in it and all that, right? But to first order, for the purpose of our discussion, we can think of it this way. Now, if I change this a little bit, right, if I move the lenses apart, now there's a gap between the two focal distances, right, f1 and f2, objective lens and ocular lens. And with this gap here, the ocular lens is not able to return the rays to a parallel configuration, right? So now the eye is not seeing light arrive in a way that the original light was arranged. And so this would result in an out of focus image. And we can get the same problematic situation, or a very similar one at least, by moving the lenses too close. Now the two focal distances are overlapping here, right? And once again, with this configuration, the eye is not seeing the incoming light arrive in the same relative arrangement that we had to begin with over here. But we can fix this by returning the lenses to this configuration where the focal points are on top of each other. And now we have restored the proper function of our light funnel, and the image is back in focus. So that's great. And yeah, so just like we said on Sunday, the takeaway here is that the distance between the objective and eyepiece lenses needs to be adjusted depending on what eyepiece and telescope you have, and your telescope has a knob to perform this function. And we can just quickly revisit this slide. This is where we actually saw the knob in the picture. Right, here's the objective lens. the ocular lens or eyepiece lens is here in this assembly, and this was and is the focusing knob. If you turn this, it physically moves this in and out, changing the distance between the lenses, changing this distance here, and you would tweak that until you achieve focus for your eyes. Okay, with that we can move on to image formation. So let's go ahead and talk about that. So here is a sample object off in the distance, and I've chosen the tree. And that tree, of course, will be reflecting or perhaps emitting, if it was some actively glowing thing, right? It will be reflecting or emitting light in many directions. There will be light going, off to the left and to the top and, straight at you. But in this diagram, I've focused on the light rays that are coming from the top of the tree going over to the right. And we can ask a question: if we put an eyeball over here, which rays do we really need to worry about to analyze what's happening? And so it would look like this. So here I've replaced the tree with just a generic object. So my arrow is representing whatever is out there. And if my eyeball is here, do I need to care about this light ray that goes up here? No, right? Because this is lost to the eye anyway. I can isolate this light ray right here. This is one that's definitely hitting the pupil. And so this light ray I can think about if I want to see how the eye is receiving light and seeing the distant object. And yeah, so then we can kind of complete the story and say, for seeing with the naked eye, we could just consider rays from the very top and the very bottom of the object, taking this path to the center of the pupil. Again, of course, there are many more rays, but these are a good representative set to allow us to think about all of it. And so, for example, if you consider the light rays that I have not drawn, but that would be emitting from the object here along its height, there would be a whole bunch of rays, but they would all be contained in this envelope, right? They would all be in this funnel going to the eye. Now, we can think about light passing through a lens. So now we have, let's say, these 4 rays to worry about. So again, top and bottom of the object, we have rays going parallel to the optical axis from the top and bottom of this object, going towards the lens. And then also from the top and bottom, we have rays going towards the center of the lens. Okay, so we've chosen these 4 rays for analysis. And if I continue the ray diagram, drawing what happens to these rays as they pass through the lens, we get this. And so here now, it looks kind of busy at first, but we can figure this out, right? So let's pick this apart. So here is the ray that started at the top of the object, was heading towards the center of the lens, and it'll pretty much just, keep on going through and take this path. The ray that started out at the top and went parallel to the axis hits the lens, gets refracted or bent here, and takes this path. And the interesting thing happens right here. So this is where these 2 rays that left together join up again, right? They meet again here. And the same thing is happening for the rays that started from the bottom of the object. They meet up again here. And so what happens then is that there's an image that forms here. Notice it's, the focal point is here, and the image is forming past the focal point. And the image is upside down, right? Because the rays that started at the top here, converged at the bottom here. And this image is called the prime focus image. And it's an image that could be projected onto a screen, or it could be funneled into an eye with a second lens, just like we built our light funnel before, right? We could put a second lens over here. In fact, we'll do that in a little bit. And then we would have, rebuilt our light funnel. So, but yeah, so the key observation here is that we end up with this image that could be projected onto a screen, and we call that the prime focus image. Now, objects in astronomy are really far away. And so, so far we've talked about our light funnel, saying that, okay, all the light rays are coming perfectly parallel, towards our lens, and they converge here and so on. And that's how we constructed our light funnel to begin with on Sunday. But you know what? Nothing is really at infinity. Even in astronomy, objects are only very far away. Sure, they may be 10 million light years, 100 million light years or farther away, but even that's not infinity. It's just a really, really big distance. So if we make this a little more accurate, it would look something like this. Now, the problem is, of course, I cannot draw this accurately because my slide here is not nearly big enough to move my object, 10 million light years to the left. So the way I've chosen to draw this here is that, the ray that is parallel to the optical axis, I have my dash, dash, dash here, which represents that we're covering a huge distance right here, right, that I cannot represent on the drawing. And for the ray that is just going straight across, that's pretty straightforward. For the ray that is starting at the top, approaching the center of the lens, I had to do this trick here, right, where dash, 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 and it stops. And then we imagine that we're traversing a huge distance until finally, this ray becomes this ray, and we're back on the drawing now, right, and then goes to the center of the lens, and the same thing is happening at the bottom. So now, with my object really far away and the light rays taking this path, notice what's happened here, right? My image, the prime focus image, has moved much closer to the focal point, right? Before, on the prior drawing, the prime focus image was like somewhere over here. But as I move the real object farther away to the left, the prime focus image creeps closer and closer to the focal point, and it becomes also very, very tiny, right? It's become very, very short. Okay. But for our purposes, we got to think about this, right? Diagrams are really impossible to draw to scale, right? Especially with astronomical distances, I cannot truly draw the right distance here, and the image would be so close to the focal point and so tiny that it's effectively impossible to draw. So this is where we're going to cheat a little bit. Let's pretend that the image does in fact form right at the focal point, and we can get away with that by saying that astronomical distances are virtually at infinity. So even though infinity is not a real quantity and nothing is truly at infinity, it's okay if we think of it that way. So yeah, okay. So with with the pretense that this thing is at infinity, then the object effectively, the image, the prime focus image, forms exactly at the focal point, and that works for our purpose of analysis. So notice here that I've drawn my upside down image arrow, really big. Of course, I've drawn it way bigger than it really is. Like we said, it would be really, really tiny, but it would be invisible if I drew it accurately. And so I'll just represent the image by this visible upside down arrow, even though that is somewhat of a cheat, but it works for our thought exercise. Okay, and so yeah, so we can complete our light funnel by putting the ocular lens back, right? And our lenses here, of course, again have their focal lengths. So notice that I've changed the nomenclature just a little bit. My objective lens here, I'm calling the focal length FT because we're going to move away from just generic objective and ocular lenses. We're going to start thinking specifically about telescopes and eyepieces. Okay, so telescope, focal length, eyepiece focal length, and specifically focal length of eyepiece number 1, because in a moment we're going to be changing eyepieces to eyepiece 2 and eyepiece 3. Okay, but yeah, so this essentially is a diagram of our original light funnel. The prime focus image forms here. In reality, it's truly very tiny, but this arrow represents it. And then the eye really ends up seeing a representation of the prime focus image through the ocular lens. And just a reminder, right, that image is inverted because the light ray that started out here, got flipped to the bottom here. Okay, so with that, let's go ahead and jump into magnification. So remember how the eye saw the original image, right? We had drawn this tree as an example and then used just this arrow as a representation of some generic object that doesn't have to be a tree. And we chose the rays coming from the top and bottom going to the pupil to say, okay, we can think about these rays as a good representation of all the rays that we care about, and then we can think about how the eye sees this image. When we put lenses in the light path, we drew a picture like this, right, where some of the rays are these, right, where it comes from the top of the object, parallel to the axis, goes to the lens, and then through the ocular lens again, going to the eye. And so one key thing to note here is, the eye is not really aware that there are lenses in the path, right? It just receives light. And then, the eye takes in that light, the brain does some processing, and the brain presents your consciousness basically with an image, right? But that optical system in your head is not really aware that lenses were put into the light path, right? It just receives some light and then perceives something about reality. And so the cool thing is, right, and that's why telescopes work, is that by putting these lenses in here, we can change how our mind, our head, right, perceives that reality, effectively making things appear brighter or larger, right? Because these lenses do stuff to the light path that essentially trick our brains, right, into seeing reality a little bit differently. And it turns out we're going to leverage that, for the purpose of how we magnify things. So we can ask, what's the equivalent of the yellow rays in the bottom diagram? Okay, and so let's think about that, right? So again, for reference, here's how the eye sees without any lenses at all, and here is our lens system. And so really what's happening is that from the eye's perspective, the rays appear to come from the prime focus image. With the lenses in the system, the eye is basically seeing the prime focus image. So from the eye's perspective, it appears that rays are coming from here and from here, towards the eye. That's the equivalent of what we had here without any lenses at all. Notice, right, that the shape of this light cone, right, that's coming from the prime focus image is much steeper. It's a much different cone than if we were just receiving light directly from the object here, right? And so what that gets us is that, if we imagine that this object that the eye is seeing, that prime focus image that the eye is seeing, if we project that back to where the object really is, the object now appears much larger, right? So yeah, so by virtue of the eye seeing the prime focus image and projecting that back to where the object really is, the object appears much larger. And of course inverted, right? Because what was the top of the object, those light rays ended up down here. But again, the key thing we're focusing on here is that the image gives you a larger apparent object. And yeah, and so this is now, if we think about the magnification here, this is what's happening. We have our telescope focal length, we have our focal length of eyepiece number 1, and I've drawn it such that the telescope focal length is 3 times the focal length of the eyepiece. And if you look over here, the way the diagram is drawn is like, yeah, the perceived size of the image is 3 times the size of the real image. Okay, so this is exactly what we said on Sunday, right? That the magnification ends up being the division of the focal length of the telescope and the focal length of the eyepiece, right? Ft divided by Fe1, which in this cartoon here is 3. If we change the eyepiece to eyepiece 2, so notice what I've done here is the focal length of the eyepiece has increased. This is an eyepiece with a larger focal length, such that the telescope focal length is twice the eyepiece focal length. So, this division here ends up being a 2. And yeah, if we look at our ray diagram, here is the real object, and the way the light cone works out, right? The way the eye perceives this image. So again, the eye really sees the prime focus image, through the ocular lens, but projecting those rays all the way back to where the real object is, that object appears larger. In this case, it is twice as large, right? The real object being here, and the projection or the apparent object, being here twice as big. Or we can go the other way, right? We can make the eyepiece focal length really small, and by doing so, it makes this cone even steeper, right? And now the apparent object size has increased, right? So the high level takeaway here is that as we make the, with a telescope focal length fixed, which is typically the situation, right? You have one telescope, or you're working with one particular telescope, you're then changing eyepieces. So as you make that eyepiece's focal length smaller, magnification increases because this light cone, this perceived light cone, becomes steeper or wider. And if the eyepiece focal length becomes larger, then the magnification decreases because this cone becomes shallower. And yeah, okay, so just to wrap this up again, with how we said it on Sunday, magnification is a function of the focal length of the telescope and the eyepiece, and magnification, or the power of the system, is the telescope focal length divided by the eyepiece focal length. And I hope that the diagrams on the prior slide make it clear how that comes to be. Okay, let's close out the ray diagram story here by looking one more time at F ratio. So remember that we talked about focal ratio, or F number, or multiple names for this, and we had this example. We said let's have a telescope with a focal length of 700 millimeters and an aperture of 100 millimeters. So here's my focal length of 700 millimeters, and here's an aperture of 100. I realize this diagram is not drawn to scale because, again, I wouldn't be able to really fit it on the slide properly. So, imagine that this is actually 7 times longer here than this, right? Because this is 100 and this is 700. And in fact, that, this 700 divided by this 100, that is the focal ratio, right? We said that the focal ratio is defined as, is this number n that's defined as the telescope's focal length divided by its aperture diameter. So that's 700 divided by 100, or just 7. And so, yeah, this is an f7 telescope, this example. And if I now change the aperture diameter, so I make the aperture larger, right? So I noticed that, I'm now, for example, in my cartoon here, I'm picking up some more light. The top and bottom rays are additional that we didn't have before. If I then recalculate my focal ratio, it is now 700, unchanged from the last slide, to the now larger aperture of 125. So then this division works out to be 5.6. And now my telescope is an f5.6. So as aperture increased, the system went from f7 to f5.6, and more light is reaching the eye. This is pretty obvious, right? Because I've actually made the aperture larger, right? So I am collecting more light, and so, therefore the image that the eye is seeing has become a little bit brighter. And for photography, an image sensor could collect light in less time. So if you previously, with the f7 system, had to, let's say, leave the camera shutter open for 5 seconds, now, with the larger aperture, you're collecting more light. Maybe you can get away with only 4 seconds of exposure. So this is pretty straightforward. So we call this a faster telescope. The f5.6 is faster than the f7 because you're actually collecting more light, thereby allowing a camera to take a picture more quickly, and even an eye will see a brighter image. This is the part that makes a lot of sense. Now here's the part that makes less intuitive sense. So let's go back to our baseline. So back to the f7 telescope, 700 millimeter focal length, 100 millimeter aperture, back to f7. Now, instead of changing the aperture, I'm changing the focal length. So this has stayed the same, but I've decreased my focal length from 700 to 560, right? So this distance here has decreased. And if I now calculate my n, the focal ratio, it is again 5.6. Okay, so now we need to ask, well, wait, does this also produce a faster telescope, right? This is where this notion of fastness, right, is not intuitive, at least not to me. So let's see what's happening. So one more time, back to the baseline, right? So we're resetting again to our, f7 telescope. And let's remind ourselves where the prime focus image is forming, right? So we ignore the ocular lens here for this conversation now. And we are just going to look at the image formed by the objective lens. And remember that this is the image here that could be captured by an image sensor, or it could be projected onto a screen, right? And this was the prime focus image that we mentioned earlier. Now, let's again reduce this focal length and see what happens, right? If I reduce that focal length, the prime focus image moves closer to the lens. It is now here. This is where it was on the prior slide. This is just shown for reference. But now the prime focus image that's produced by the system with a shorter focal length has gone here. And so notice it's become smaller, right? It was this big before. Now it is shorter or smaller in area, which means that the light has become more concentrated, right? Whatever light I had here before, it's still the same total amount of light, but it has become concentrated in a smaller area. So for a camera sensor, an individual pixel will actually see more light, right? From a perspective of a single pixel on a digital camera sensor, more light is received there, right? And so therefore, yes, the sensor can capture the image in less time, and it's again a faster telescope. So I hope that made sense, right? So again, we're not collecting more light, but from the perspective of an image sensor, we've concentrated that light more, and that's why imaging can happen more quickly, and we consider this a faster telescope. So just to kind of review this one more time, and with slightly different numbers here, focal ratios tend to vary between f15 and f5, right? So this is a typical range for amateur telescopes, and a telescope with a lower focal ratio like f5 is typically called a fast scope. And then we have two ways of getting to a fast scope, right? One is, say, we can assume that we have a fixed focal length of 500 millimeters, but the aperture varies, right? We go, let's say, from a 50 millimeter aperture scope to a 100 millimeter aperture scope. And that means that the telescope with 500 millimeter focal length and 50 millimeter aperture is an f10, and the one with the same focal length of 500 millimeters but 100 millimeter aperture, now larger, becomes an f5. And so yeah, so with that larger aperture, more light is collected per unit time, like per second. Light is collected more quickly and the scope is faster. And then the other one, the less intuitive one, was that we keep the aperture fixed, but we reduce the focal length, right? And this is the one where we're saying we're now concentrating the prime focus image more, and because light is more concentrated from a perspective of a camera, it is also a faster scope. So I hope that made sense. All right, we made it through all the ray diagram stories. Let's talk briefly about eyepieces. So I showed this on Sunday during our in-person session, but let me just kind of pick it up again here for context. So these were both 12 millimeter focal length eyepieces. Okay? And we said that, hey, this one is $30 and this one is $80. So clearly something's different, right? And they're charging you more money for the one on the right. And things that are different are, for example, the apparent field of view, right? So this one has a 50-degree apparent field of view. This one has 60 degrees, meaning that when you look through the telescope, the eyepiece on the right would give you a larger image circle to see. The other thing different is the eye relief, 8 millimeter to 16, which means that this eyepiece allows you to have a little more comfortable viewing position. You don't have to smush your eye quite as close to the lens element here. And especially for eyeglass wearers, right, you might be able to fit your eyeglasses in between your head and this eyepiece much more comfortably than over here. So these are really the two primary differences, that you get for the extra $80. Internally to the lenses, the extra $50, right, going from 30 to 80. Internal to these eyepieces, there's a difference in lens elements. So this one has 4 lenses inside the housing. This has 6. And from the outside, that really doesn't matter. But it's the extra lenses that ultimately work out to give you the extra field of view and the higher eye relief. So these were all more or less the same type of eyepiece in terms of focal length. 12 or 11 or 13 millimeters, give or take one, is effectively the same. Doesn't make a big difference. But we're going in price all the way from $30 to $630, right? And even actually check out these two, right? So this guy here and this guy, notice that their specs are basically the same. 50 degrees apparent field of view, 8 millimeter eye relief. Yet this one is 3 times as expensive. And so what's happening here is that this is just a premium brand. This is a consumer brand, mass production. This is, a higher end brand. And so, with this money, you're presumably buying an eyepiece that has better quality glass, better quality optical coatings, and presumably, higher assembly quality as well. And these are pretty nice eyepieces. And you can see that they are from the same brand. We have these others here where you go from $95 to $320 to $630. And as we climb this here, right, what we get for the money is increased field of view, all the way up to 100 degrees, and the eye relief increases, 8 millimeter, 12, and 15 millimeter. So this is very expensive. You don't usually need these eyepieces when you're starting out, but they are really nice. So eventually, maybe you choose to invest in one of these. And, it does give you a view, like I imagine it would look if you just pressed your nose against the porthole of the International Space Station. It feels very immersive, one of these things. So they're very cool in that regard. But they're also really big, and they're big and heavy and expensive. Here's another example of how eyepieces are sold. This is, for example, a company called Explore Scientific. And notice that they have lots of different series of eyepieces. They have, these are all apparent fields of view, right? 52 degrees, 62, 68, all the way up to 120, right? So for each of these series, there's a bunch of different focal lengths, and you have to choose what you want to buy. So for example, here is the 62 degree series. I'm showing a 26 millimeter focal length eyepiece, apparent field of view 62 degrees, eye relief 19 millimeters. And it's 95 pounds, excuse me, it's half a pound and weighs, it weighs half a pound and costs $95. Then over here, this is the 100 degree series example. Again, about the same focal length, 25 versus 26, almost the same. But apparent field of view 100 degrees, right? So you get that immersive experience. The eye relief is actually shrunk a little bit. It does require a larger barrel. So you have to make sure that your telescope can accommodate this if you want to buy this eyepiece. And also it's much heavier and much more expensive. So the point here is that, there's a huge number of options, and you will have to think about where to invest. What do you care about? Do you care about cost or focal length? You'll always want a collection of focal lengths. We'll talk about it a little bit more in a second. But you'll always, with the focal lengths that you do want, you can then choose, do I want a small field of view, a large field of view? How much money do I want to spend? How important is eye relief? Things like that. And just to close it out, let me review briefly the zoom thing here, right? We said on Sunday already that you can purchase these zoom eyepieces where you turn part of the eyepiece like this ring right here, and that changes the focal length of the eyepiece dynamically, and you can zoom in or out just by turning that. The ranges are 24 to 8 millimeters for the focal length in both of these eyepieces. The apparent field of view is better, larger over on the right, and that's partly why you pay $290 over here and $80 here. Again, these prices are actually from 2019, so today it might be a little different, but this is intended to show the relative difference. Okay, so yeah, so that money buys you some more apparent field of view. The eye relief is actually a little smaller here, so that's actually worse. But overall, this does have better optical quality, so you'll probably get better images out of this one as you would over here, as long as the eye relief works for you. So again, there are trade-offs to make, right? You have to decide, what is most important to you. And zoom eyepieces can be convenient. In some ways, they're great, but remember that all else being equal, a single focal length eyepiece tends to be better, tends to provide a better view. So, for example, if you want to look at something and you need a 24 millimeter focal length eyepiece, a dedicated 24 millimeter eyepiece will probably give you a better view than a zoom eyepiece set to 24, just because they're always engineering trade-offs, right? When you're creating an adjustable device, there's some trade-off, right, where you're sacrificing some image quality perhaps, right, for the benefit of having this adjustable thing. But again, zoom lenses can be great, so go ahead and try them out and make your choices. Let's talk a little more about Barlow elements. So this is related to eyepieces, and I consider these eyepiece accessories. So we said a Barlow lens is a thing that fits between the eyepiece and the telescope and increases magnification. So the way it does that is by reshaping the light path to effectively increase the telescope's focal length. And so this diagram illustrates that. So element A here is essentially the telescope's objective lens. In this case, they've drawn a doublet that we also call an achromat when we had the refractor conversation on Sunday. And so if the light arrives parallelly here, this lens element bends the light, and the focal point would be here at the tip of the red lines over here. This is when, if the Barlow element were not in the path. But now if we put this element B here, which is the Barlow lens, it bends the light a little bit such that the light actually converges over here. So effectively, it has made the focal length of the entire system longer than it was before. And remember that magnification is the telescope's focal length divided by the eyepiece focal length. So if the telescope's focal length becomes larger, that division produces a larger number, so therefore a higher magnification. So Barlow lenses come in various configurations, typically 2x or 3x, meaning that if the focal length here is, let's say, 1,000 millimeters, and I put a 2x Barlow in it, then the telescope behaves as if the telescope's focal length is 2,000 millimeters. Here's some examples of Barlow lenses. I think we showed this on Sunday, but just to put it back in context, this is a 2x lens, this is a 3x lens. They actually cost the same amount of money, but this one will make your telescope's focal length appear as if it's 3 times the actual. Over here is another 2x Barlow lens, but this one has a 2-inch barrel, so the difference is in the size of the barrel down here. And it's more expensive in part because the lens in here needs to be physically larger because it's accommodating a larger, optical path, through the element. The opposite of a Barlow lens is a focal reducer. So focal reducers are also called telecompressors. Effectively shorten the focal length of your telescope. And the typical reduction is like 0.7x or sometimes 0.63. So what that means is that with a given eyepiece or camera, it results in lower magnification and effectively a wider field of view, just because it doesn't make the image circle any bigger, but it's shrunk what's in the image circle, so you're seeing more. And sometimes this is what you want, because again, some sky objects are actually really large, and so you want really low magnification, and this can help you get there. So a reducer typically attaches to the telescope too, so it's really more of a OTA than an eyepiece accessory, but it does kind of fit into the whole discussion of eyepieces and Barlows. And yeah, so this is an example of a reducer, and it would connect right here, right at the back of the telescope to before the rest of the eyepiece assembly. You can see here, this is reducer is a 0.63 reducer. This is 0.7. Price difference is pretty significant here, 190 to 410, even though these are both for the same size telescope, but the difference is this Edge HD thing. You may remember from our examples of Schmidt-Cassegrain telescopes on Sunday that Celestron is a brand that sells kind of standard or regular typical telescopes, and then their Edge HD line. The standard line has this problem of field curvature, which you don't want for photography. The Edge HD telescopes have an extra optical element in the tube assembly here that produces a flat field, which is great for photography, and you can maybe even see the benefit with the naked eye sometimes. But because the things have gotten more complex for maintaining a flat field, this reducer is much more expensive, because it has to have more optical elements. There's more complexity here to maintain that flat field, and so therefore this guy is more. So make sure that you buy the right one, right? Depending on whether your Schmidt-Cassegrain telescope is a standard or Edge HD, make sure you purchase the right reducer. Okay, so let's do kind of a very quantitative example here, considering some eyepieces and Barlow lenses and reducers. So we're going to use the Celestron XL LX eyepiece series as our baseline. So if you go shopping for telescope parts, you will, for example, see this eyepiece set, right? And you can buy these types of eyepieces in any of these focal lengths: 2.3, 5, 7, 9, 12, 18, and 25. And one interesting thing to note here, by the way, is how the steps work. So from 2.3 to 5 is 2.2x, from 5 to 7 it's 1.4x, and then you can see 1.3, 1.3, 1.5, 1.4. So most of these steps are actually essentially the square root of 2. So yeah, this is pretty common, so that the focal lengths are stepping in increments of square root of 2 or thereabouts. And what that means, or the reason this happens, is that these steps of square root of 2 correspond to an object area scaling by a factor of 2. So in other words, let's say you're looking at the moon, okay? And you're changing eyepieces, let's say from 12 to 18, right? So going from 12 to 18 will reduce magnification, right? Because you've made the eyepiece focal length longer. And so now you've taken the moon's area and you've scaled the area down by a factor of 2. Okay, so moon's area has become half of what it was before. Not the linear dimensions, but the area. And along with that, the brightness, the effective brightness also changes by a factor of 2, because as you scale it down, the light becomes more concentrated. Or on the flip side, if you were to scale it up, then the light becomes more spread out and the brightness changes. Okay, but let's say we go shopping and we buy these eyepieces. We buy a 7, an 18, and a 25. We do not buy the 2.3, 5, 9, and 12. Okay, so our shopping basket has in it these three right here. And we're also going to go shopping for the Barlow lenses. We're going to buy the 2x Barlow, the 3x Barlow, and the 0.7 reducer. So we go crazy here, right? We buy all the parts. And now the question is, if I combine these, what do I get, right? If I combine eyepieces with these Barlow or reducer elements, what do I end up with? And that's what this initially busy table is showing. So here are all the eyepieces that I have purchased, and here are the Barlow and reducer elements I have purchased. And if I combine them, these are the effective focal lengths of the eyepiece. Okay, so if I take my 25 millimeter eyepiece and I combine it with the 2x Barlow, my telescope system behaves as if I was using a 12.5 millimeter eyepiece. Okay. Similarly, if I have my 18 millimeter eyepiece with a 2x Barlow, together they behave as if the eyepiece is a 9 millimeter eyepiece. Earlier, I put this more in the context of the telescope's focal length, saying that a 2x Barlow behaves as if the telescope focal length is doubled, and that's still true. But we can also think of it a little differently. We can think of it as the Barlow, dividing the eyepiece focal length by a factor of 2, and that's how we're thinking about it here. So what we end up with then is we get all these effective focal lengths, through all of our combinations of eyepieces and Barlow and reducer elements. But they're not all interesting, right? Because notice we've gotten, for example, 25.7 here, right? If I take my 18 millimeter eyepiece and I combine it with the 0.7 reducer element, my effective eyepiece focal length feels like 25.7. Well, that's almost exactly 25, so it's not interesting, right? If I want to have that focal length, why wouldn't I just use the 25 millimeter eyepiece all by itself instead of making it complicated using the 18 millimeter with this reducer? So the blue ones here are basically redundant, right? They are not helping us at all because the 6 is too close to the 7. Again, the 8.3 is too close to the 7. It's a little different, but not appreciably so. The green ones, they are interesting, right? They are different, right? So 9, 3.5, 2.3, these guys are actually useful additions to the effective set of focal lengths. So yeah, so many of the additional generated effective focal lengths are useful, but some are not. So this is something that you want to think about when you go shopping. You essentially want to consider, what do you end up here and what do you get here given all the eyepieces that you have or want to buy and given the Barlow or reducer elements that you want to buy. Make sure that you don't buy stuff that gives you lots of useless redundant combinations. You want to make sure you maximize the various useful combinations. And so, yeah, so we started out with, just these 3 eyepieces, and then we added the Barlow and reducer set to it, and that gives us an effective set of focal lengths that also include 2.3, 3.5, 9, 12, and 36. So by buying, 3 eyepieces and 2 Barlows and 1 reducer, we effectively have 1, 2, 3, 4, 5, 6, 7, 8 eyepiece focal lengths. That could be good. But again, think about it, right? So that there are trade-offs in play here. And one of those additional trade-offs is that by adding elements to the optical path, you may degrade the image quality. Okay, so every time we add any kind of glass, more lenses, something to the optical path, you might lose some light, you might scatter some light. And, so all else being equal, using, this 2.3 millimeter eyepiece, if you actually buy this, you probably get a slightly better view than if you use the the effective 2.3 millimeter eyepiece that we get over here by taking one of the other eyepieces and combining it with the Barlow. Do you notice the difference? It depends, but just be aware there may be some impact. So think this through. Don't go nuts buying eyepieces and Barlow lenses. Think about what focal lengths do you want. What's your budget? How do you best get there? And there are choices to be made. Okay, let us jump forward to mount mechanisms. So now we are going to be in the world of telescope mounts, where we said that we have 2 types of basic mount technologies, alt-az, right? This was altitude azimuth mounts, right? Where you have these 2 axes for position the telescope. And then we talked about equatorial mounts, which are a little bit more confusing because the whole thing is kind of tilted so that one of the axes aligns with the Earth's axis of rotation, and there we call the axis right ascension and declination. But regardless of whether it's an alt-az or equatorial, the drive mechanisms for these mounts typically include some gears and perhaps electric motors. And even this guy here, right? This one does not have motors, but it still has gears, right? There are still gears between the hand adjustment here, right, and the rest of the mechanism. So gears are often in there, motors sometimes if it's a driven, automatically driven mount. And so those mechanisms have two important mechanical properties that you want to be aware of. One is called backlash, and another is called periodic error. So one question we want to ask is, how much back and forth wiggle is there when a mechanism is ostensibly holding position? So let's say you're actually trying to hold the telescope perfectly steady, just not moving at all. But do the gears actually have a little bit of jiggle in them so that even though the gears are not really, the drive gears are not changing, is the telescope still possibly jiggling a little bit? Another way to ask that same question is, how much dead time, in other words, time of no motion, is there when the drive mechanism is reversing direction? And this diagram here tries to illustrate that, and then I can also illustrate this by literally kind of hand waving here, right? So let's say this is the driving gear, and this is the driven gear. And so if this gear is trying to drive this gear, they would make contact here, and one gear would push up the other one like this. But now what if we reverse direction here? Notice that if my drive gear reverses direction, for a little while nothing happens until they touch again here, and then the driven gear starts to move. And that is basically what this is trying to illustrate as well. And this slop here, that is what is called backlash. And that is what would cause wiggle up here or dead time down here. And this backlash can cause confusion during alignment of go-to telescopes, and it can cause imprecision when locating a new object, when your scope is trying to find some new object, because it's basically error or uncertainty in the mechanism. The other one is periodic error. And here the question is, how much wobble is there as the gears of the drive mechanism go through a full revolution? So gears are, often circles with teeth. Sometimes there are other structures like things called worm gears. But regardless, let's think of a circular gear with teeth, for the purpose of understanding this. No matter how carefully you create or build such a gear, it'll never be truly perfect, right? It may be a little bit out of round. Some teeth may not be perfectly shaped. And so as that gear goes through its cycle, somewhere there's going to be a little error where, the teeth grab a little sooner or a little later than you really want them to. Okay, and that would be periodic error. As the gear goes through its cycle, it is not driving consistently, uniformly all the way through. Somewhere it might drive a little faster, somewhere just a little bit slower. These things are tiny, and they're relevant for visual astronomy, but the error may actually be significant for astrophotography because it might cause blur during long exposures. So periodic error, the good news is you probably don't care for visual, but you'll see a periodic error spec when you go mount shopping, and it does matter for photography. And there are ways you can compensate for it, but that also creates more complexity. And so, ultimately, it's important to understand if you want to do photography. I also want to talk briefly about positioning resolution. So for computerized mounts, two additional factors come into play: positioning resolution and position sensing. Resolution is the following, right? So the computer divides the sky into some number of discrete steps. Remember, we said much earlier that, on Sunday, we said that the sky is basically 180 degrees horizon to horizon, right? And we measure the size of sky objects in degrees. And so, the computer needs to be able to understand this whole space, right? So it will understand this as some number of steps. And we can kind of go to an extreme to make this obvious. Let's say the computer divides the sky into only 4 steps. So in other words, here, 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 and here. Well, if we're now trying to find an object and the computer only understands the sky as 4 steps, then it's going to be really difficult to accurately point to almost anything, right? But the more steps the computer has, the smoother the whole thing will be, right? And the more accurate and precise it can be. So yeah, so greater the number of steps, the more precisely a mount can find and track objects. So you like to have a mount that has a high resolution. The other part here is sensing, and the key takeaway here is that most mounts do not actually sense their position. They don't really know where they're pointing. Initially when you do mount alignment of a go-to scope, we said that you will show it 2 bright stars, right? You say, okay, let's see, over here is Polaris, and over here is another one, and those are the reference stars that the computer and the whole mechanism uses to find other things. So the computer would say, okay, the object that you've asked me for, I know it's 1,000 steps to the left from Polaris. And so based on that, it basically says, okay, here's Polaris, and let me just count 1,000 steps to the left. It doesn't actually measure where it's pointing. It's really just, counting steps and hoping for the best. And that tends to work pretty well, but it's not perfect because again, the mount doesn't actually know where it's pointing. It's just assuming that counting the steps will get it to where it wants to be. Higher end mounts will have devices called encoders to actually measure the position, and we call that closed loop control. So over here it was open loop control because there's no real feedback of where the mount is pointing. We're just counting the steps. Over here there is feedback on where the mount is pointing, and so we call this closed loop control. So if you're really interested in astrophotography, again, this may be important. This may be interesting for you. So this resolution and sensing, applies to go-to and push-to mounts. Actually, go-to mounts, resolution and sensing apply, and push-to mounts rely really more on sensing, right? So to be able to push a mount to somewhere, there has to be some way for the mount to know where it is, to sense where it is pointing, so it knows whether you've pushed it to where you wanted it to go. So anyway, it's good to understand these concepts because they become important as you make your whole astronomy setup fancier, perhaps to accommodate astrophotography. Okay, let's jump forward to strain wave mounts. So these are a category of often equatorial mounts, but they sometimes you can also find alt-az mounts that use this technology. And it's really not a new technology, but it's new to the astronomy consumer market. And here's an example of how a strain wave gearing mechanism works. It's kind of a cool animation. We're not going to spend too much time on this. You can read more about this if you like. It's pretty neat. But it's fundamentally, this kind of unusual looking gearing mechanism that gives us the benefits we'll talk about on the next slide. Note that the strain wave mount technology is also sometimes called harmonic drive technology. This is more of a trademark, but you may see that as you explore options online. So strain wave mounts kind of look like what we called center weighted mounts. On Sunday, it's a type of equatorial mount, but without the counterweights. That's a key difference here, right? The other types of equatorial mounts we saw, they had a counterweight bar, sticking out here with a heavy counterweight perhaps, but on these mounts you don't have that. And so while these mounts are more expensive than traditional equatorial mounts, strain wave mounts have attractive advantages. So like we said, no counterweight, although sometimes you can still add a counterweight to achieve more carrying capacity, but you can get away without a counterweight for a lot. And then overall, this technology might give you a device that's slightly lighter than traditional equatorial mounts, so it's easier to transport and set up. These guys have virtually no gear backlash. So we just talked about backlash, right? And these strain wave drives are really good in this regard. And they often also have relatively low periodic error, so good for imaging. Here are some examples. These two are from the same manufacturer, but they differ in terms of their weight and carrying capacity, the payload capacity. So this guy is 3.9 kilograms, this guy weighs 5.5, so heavier to carry around, but for that you get a higher payload capacity of 15 or 20 kilograms. So notice the difference here is, again, depending on counterweight. If your telescope setup is 15 kilograms or less, you can use it just like it looks here. But if you want to put a little heavier stuff on your mount, right, if what you put here would be bigger or heavier, then you could still add a counterweight bar to make that work. Here's yet another one that has an even higher payload capacity, at higher expense and higher weight of the device itself. But these are pretty cool, so something to research and consider. The final thing I want to mention here is equatorial wedges. So this is another way to get an equatorial mount effectively. I haven't seen these too much in my time in amateur astronomy. I think maybe once or twice somebody had something like this, but it can be a good option if this works for you. So notice that what we have here is a tripod, and then this thing, which is basically one of the alt-az Celestron telescopes we saw in earlier slides on Sunday. But what's new here is that this thing got shoved in between the tripod and the rest of the mount assembly. And this wedge, can be tilted to various angles. such that we are aligning again one of these axes to the Earth's axis of rotation. So this effectively allows you to convert your alt-az mount to an equatorial mount. It's a little more complex because you have this extra part to carry around. You have to assemble all this, but for some people and some use cases, this can be a good option. So you may want to check into that if you think you might like that. Okay, let's jump to finders. All right, just to kind of refresh here. So we talked about magnifying and non-magnifying finders on Sunday. Non-magnifying finders are useful for finding bright objects because the non-magnifying finder, projects these circles onto the sky. And if you just put that bright object in the center, it's super easy, and then you'll have it in the center of the telescope, and you're good to go. And this is basically what you want to do when you're aligning your automatic mounts, right? You want to put some bright reference star in the center, and then just look through the telescope, fine-tune it perhaps. But these kinds of non-magnifying finders make that pretty easy. And they also facilitate a way to find objects. It's called star hopping, because this bullseye pattern actually has a certain calibration where, this inner circle is like 1 degree of sky, and then it's like 2 degrees to go over here and 2 more degrees to go over here. So for example, if you have a bright reference star and you know that, let's say a galaxy that you want is, let's say 3 degrees over to the left, right? You can use these circles to tell you like, okay, 3 degrees is got to be about here. Magnifying finders are useful for locating fainter objects that are not close to bright stars, right? Then the magnifying finder can help you, see a faint fuzzy and center your main scope, that way. But regardless, all finders need to be aligned to the optical axis of the main telescope, and that's why you have adjustment screws. Here you've got these 3 white screws, and you have to fiddle with those, to get in this case, a non-magnifying finder, to get the bullseye pattern, properly aligned so that the center of the bullseye matches the center of the field of view of the telescope. This can be a little tricky the first time you do it, but you'll learn it, and you could easily get some help. A new type of finder that we didn't talk about on Sunday is a plate solving finder. So let's see, there's one more way to figure out where to look, right? And that method is to take a photo of the sky, match the stars in the photo to a map of the entire sky. And once you've found a match, you know exactly where you're looking. And if you know where you're looking, then you also know where other objects must be in relation to where you are already pointing. So now, of course, this process of matching the photo against the star map is not easy, but hey, we've got computers, right? So we call this type of finder a plate solving finder. And yep, it's a computer that follows this process. And the term plate solving comes from old days when astronomy photos were taken on glass plates. For example, if you go visit Lick Observatory on Mount Hamilton, and if you can sweet talk your way into them showing you the archives, they have old glass plates of old astronomy photographs. It's pretty neat. And so that's where the term comes from, right? Because you would look at a glass plate, you would see a star field, and then you would try to match that against the star map to see where you were looking, for example. So so this process of doing the plate solving is complex, but computers are pretty cheap now. And here's an example of one of these. Or rather, I'm sorry, you find them in multiple devices now because they're relatively cheap. And they can be integrated into smart telescopes, like a C-star or a unistellar. They are often integrated into other astronomy imaging equipment, and they're also available as add-on devices for visual instruments like binoculars and telescopes. And here's that example. So this is a Raspberry Pi. Some of you may be familiar with this kind of credit card sized computer. You can buy them for hobby projects. And in this case, somebody built this device out of a Raspberry Pi, which has a camera and database and fancy software inside that can figure out where you're looking, right, and can tell you where the object that you want is located. So these can be quite interesting. One more finder I want to quickly mention is a laser finder. So a laser finder is a green pen laser, and here is that pen laser. And you can attach it to a telescope in a way that allows its beam to be aligned to the scope. Because like we said earlier, all finders have to be aligned to the telescope's axis. And so here, this assembly with the rings is that mount. You can adjust these screws to twiddle where the laser is actually pointing. And there are two use cases, or two ways these lasers are used for as finders. One is for showing someone where something is. So the flow here would be that you find the object some other way, you look through the scope yourself, or maybe you show the view to somebody else, and then you can turn on the laser to show where that object is in the sky. So for example, let's say you're showing somebody, a globular cluster, M13, a nice globular cluster, and somebody's asking, hey, where is that in the sky? Because you can't see it naked eye. Then you could turn on the laser and say, pew, it's right there, right? And the laser would point to the place in the sky where you are looking. And so, yeah, so we do that sometimes at public star parties and outreach events to illustrate where objects are in the sky. The other use case, which I think is pretty rare, is to turn on the laser first, swivel the telescope so that the laser points to your desired target, then turn the laser off and then look through the scope. But this really requires that you can find your object in the sky by eye, right? You have to know where the laser needs to be pointing to see the object you're trying to find. And if you can do that, you're actually better off, I think, using a non-magnifying finder like the a bullseye finder that we saw in the prior slide. Because lasers need to be used carefully and responsibly, right? Don't shine lasers at eyes directly or through reflections. Don't shine them in directions of airplanes. And don't use them if others are doing astrophotography, because you can ruin somebody's image just with a split second of a laser beam. Okay, and with that, we will close this out by quickly visiting optical filters and collimating tools. So optical filters exist in two categories, visual and imaging. Imaging filters are for use with astronomy cameras and specific imaging procedures, and we're not going to talk about them here because it's beyond the scope of this presentation. But visual filters are interesting to us today. They generally attach to the eyepiece. You screw them into the barrel at the bottom, and they come in 1.25 and 2-inch sizes to match the 1 1/4 and 2-inch barrels of eyepieces. Here are some examples. One filter that we actually mentioned earlier during the conversation on Sunday is a fringe killer or apo filter for achromats. Remember that a doublet or achromat does a pretty good job of converging all the light in one point, except the bluish purple light, right? Might be a little bit off, giving your image kind of a purplish tinge. And you can use an achromat fringe killer or apo filter to throw away that bluish purplish light so that the image looks cleaner. But you are throwing away some light, so it's not the same as the apochromat, if you remember the conversation from Sunday. But yeah, if you have an achromat, this might be a filter that you want. If you're observing the moon is super bright, and you almost certainly want what we call a moon filter, which is really something more generically called a neutral density filter. And 0.9 here means that this filter will throw away 90% of the light and only let 10% through. Even that way, the moon will look pretty bright. And so you might want that kind of a moon filter. For something like a emission nebula, something like the Lagoon or Orion Nebula, these things are star-forming regions that are pretty neat to look at. Something like a narrowband filter can be quite advantageous. So these are a little more complex. Over here, this diagram kind of shows what's going on. These are the wavelengths of all the colors on the rainbow, red light over here, blue purplish light over here. And this curve is what the filter is passing or blocking. So you can see that the filter is passing some of this red light. It's going to block all these colors. It's going to pass some of this light here, and then it's going to block all this. And what's happening here is that the filter is passing the kind of light that we know is coming from these nebulae, and that allows us to see those nebulae in much better contrast. So these filters can be pretty neat. If you like to look at Jupiter, something called an ADA blue filter might be nice. They're pretty inexpensive, and they make Jupiter look blue a little bit, but they improve the contrast between the planet and its dark cloud bands. So it can make the cloud bands much more visible, which can be fun. So out of all these, this would probably be the most expensive filter option, but might be a worthwhile investment if you like these kind of nebulae. If you like to look at the sun, there are options for you there, right? So the sun can be a great target that people sometimes neglect, right? But there's a lot going on the sun, but of course you need the right kind of filter so that you don't burn your eyeballs to a crisp. So for viewing sunspots, There are a couple different filter options. One is called an aperture solar filter. They may be made out of glass, look like this, and it just basically sits on the objective end of your telescope, like your refractor or your SCT. There's also an option to have these kind of filters with mylar screens. They're pretty delicate, but they can be nice because they are more color accurate, whereas the glass option often gives you a kind of yellowish image of the sun, whereas the sun is really mostly white when you look at it without color distortion. An alternative to the aperture filter is something called a Herschel wedge or solar wedge. Essentially, it's a special type of star diagonal. It looks like a star diagonal, but it has some different stuff inside to allow most of the sunlight to be dumped to a heatsink, so it does not go to your eye, and only a tiny fraction will safely go to your eyes. But notice that these wedges are really only appropriate for refractors. They are not a good match to an SCT, to a Schmidt-Cassegrain telescope. Beyond sunspots, you may also want to look at solar prominences. And so, here's a couple example. Do you see this little, hedge-looking thing, on the edge of the sun? Looks small, but keep in mind that you can fit 109 Earths across the sun, right? So even this smallish thing is actually pretty big. And we call this a prominence. Sometimes people think of this as a solar flare. Technically, a solar flare is something a little different. But these things can be fun to look at, and they change all the time. The sun is pretty busy, and every time you look, it's a little different. So there are these features, there are these things called filaments that can be interesting. We're not going to talk about the science, but there's a lot to see and learn, which can be fun. And if you want to see these things, you need some special hydrogen alpha filter. It's called an Etalon filter, and there's also usually another filter called an energy rejection filter as part of the whole filter solution. And these filters are quite expensive. You get them in dedicated telescopes made by places called Coronado and Lunt. I think Coronado is defunct at this point, so Lunt may be your only option. But you can buy telescopes here that are specifically for solar observing. And there's also an option to buy a specialty eyepiece. Now this is $1,000 or more eyepiece, but it has one of these special hydrogen alpha filters in it. Please be advised here that you don't want to use an H-alpha filter that is an eyepiece filter, right? So you can find H-alpha filters that kind of look like this. Do not use that for solar observing. It is not intended for that, and nothing good will come of it. So you must not use a nighttime H-alpha filter for solar observing. Be aware that filter kits may look attractive when you're initially shopping for this kind of stuff. You might come across filter kits. They look really neat, lots of options in there, but they're often not worthwhile, the investment. So, think twice before you buy that. You may be better off just buying the filters that you really need and really want once you know what that is. You'll also come across light pollution or sky glow filters. These tend not to produce good results, so I would also say don't spend money on those, or at least not initially. These things worked much better when street lights were using sodium vapor lamps. You may remember years ago, street lights were often yellow, but now we use these very white, broad spectrum LEDs, and so these filters don't really help with the LED street lamps. Finally, you may run across a Mars filter. These can be fun, but be aware that they kind of require the seeing conditions to be already pretty good. So they're not going to make a crappy Mars image look better, but if you already have a good Mars image, a Mars filter may actually really help you reveal more detail, which can be fun. And to kind of close this out, let's quickly mention collimating tools. As we discussed on Sunday, some optical devices need to be collimated, and that's the process of aligning optical elements like lenses and mirrors so the light takes the intended path. And without proper collimation, objects will appear distorted, like stars may not focus to a pinpoint, right? They might look like this with this weird looking tail here, which we call coma. Different telescopes have different needs. Newtonian reflectors, like Dobsonians, may need frequent collimation. The primary mirror gets jiggled out of position pretty easily, and so you may have to tweak it a little bit before almost every session sometimes. Refractors typically hold their collimation really well, unless they are really mishandled. And Cassegrains, like an SCT, may need to be collimated after an especially bumpy transport, for example, shipping. So it's not uncommon that you buy your brand new SCT, it arrives at your house, and it's out of collimation. So before you really get to enjoy it, you have to collimate it, and you may want to get help from a local astronomy club for the first time that you do that. For a Newtonian reflector, you may want to get a couple of accessories that help you collimate. One is called a Cheshire collimating eyepiece, or alternatively, you can get something called a laser collimator. So these can be quite handy and beneficial if you have a Dob, for example. For SCTs, these things do not work. Don't buy this, don't spend money on this if your telescope is a Schmidt-Cassegrain. For an SCT, you can buy a different kind of fancy laser collimator. This is a few $100. It looks pretty complicated, but typically collimating against a bright star in the night sky is perfectly adequate. So don't go buying this. You probably don't need it. And if you have to collimate during the day, then you can buy something called an artificial star projector. So this is something you put off in the distance, and it simulates a bright star for collimation exercises during the day. And just so you kind of know what we're talking about when we discuss collimation in general, right? A collimation test for a reflector with a central obstruction involves looking at a bright star and then defocusing that star slightly. So when the star is defocused, you'll see something like this. This hole is actually a shadow of the central obstruction. And the starlight ends up fringing kind of in this donut around it. And if you see this perfect kind of donut, then your telescope is actually well collimated. But if your donut is squished to the side, then you are not in good shape, right? And your telescope is in need of collimation. So yeah, you look at a bright star, defocus that star, and then you check the donut. And the collimation process may feel daunting because you have to adjust some screws here or there, right, to get this from here to here. And that sounds simple, but it can be confusing the first time you do it. So you can get help from your local astronomy club, and don't worry, you'll get it with a bit of practice. And with that, we are done. We have made it through all the extra tidbits here. I hope you found something useful and interesting in this extra content. Thanks again for sitting with us on Sunday, and thanks for listening to me jabber as I went through the extras. And with that, so go look at the stars and use your telescope that also happens to be a time machine. Thank you very much, and hope to see you at an SJ event, and enjoy.